Okay, in this video we're going to talk about change of basis. We're talking about change of basis with respect to linear maps. Now, remember, if you have a linear map and you have a pair of bases, you have a basis for the codomain, or basis for the domain rather, and for the codomain, that leads to a matrix. Okay. Now if I have the same linear map and I have a different basis, so I'll say basis prime for the domain and the codomain, that will give me a different matrix. So the question is, what is the relationship between these two matrices? Now, of course, that's going to depend on the relationship between these four bases: the original basis of the domain and codomain, and the primed basis for the domain and codomain. So we'll flesh that out during this presentation. Okay? So changing representations of vectors. Remember, representation of vector is the coordinates of a vector relative to a fixed basis. Okay. So that's what we're going to talk about. If we go from one basis to another basis, how does that change the representation of vectors? So we'll have the vector representation with respect to the original basis and the vector representation with respect to the prime basis. What is the relationship between these two vector representations? All right, so we will see. Now, coordinates vary with the basis. This is the point that I just made, and let's nail this point down with an example. So let's consider the vector v in three-dimensional space. So we'll start with the vector 1, 2, 3 with respect to the standard basis and with respect to this other non-standard basis. With respect to the standard basis, the coordinates of this vector are simply the components of the vector. This is the same as 1 times E1 plus 2 times B2 plus 3 times B3. E3 rather. 1 times E1 plus 2 times E2 plus 3 times E3. Now with respect to this other basis, it's a little more difficult to see. We do know how to solve this by setting up a matrix equation, but you can verify that this vector here can be expressed as 0 times B1 plus 2 times B2 plus B3. Let's check the first component. 0 times 1 plus 2 times 0 gives me 0, plus 1 times B3 gives me 1. So the first component checks out. You can check the others similarly. Now, how do you get from this representation to this representation? So that's the point what we're going to do now. Okay. Let's think about this translation in terms of an arrow diagram. Okay. If we have a vector space with respect to a particular basis, and we want to represent the same vectors with respect to a different basis, well, they're the same vectors, so we can consider this as an identity mapping. We're not changing the vectors, we're only changing the basis. Okay. Now, so the change of basis matrix for bases B and D is the representation of the identity map from a vector space to itself with respect to those different bases. And by using what we've seen before, the representation of the identity map with respect to these two bases is a matrix consisting of columns, and the columns are the representation of the original basis vectors, the B basis vectors, in terms of the D basis. All right, let me relate this back to what you've seen before. If we go to the text on page 205, you'll see this definition. If we have V and W as vector spaces of dimension n and m with bases b and d, and H from V to W is a linear map, and I've seen this before, you take H of each basis vector in the domain and find its representation with respect to the codomain basis. And you do that for every one of the basis vectors. Then these representations form the column of the matrix representation. Now in the current case, this mapping H is simply the identity. Okay. So we're just taking the representation with respect to the codomain basis of the original basis. Right. So these would simply be the representation with respect to beta 1, representation of beta 1 with respect to D, so that's this column. The representation of beta n with respect to D, that's this column. So that's exactly what we have in this case. We have the columns of the matrix representation of the identity with respect to two different bases are given by the representation with respect to the second basis of the basis vectors in the first basis. Okay, so this relates to what we've seen before. Okay, this result supports the definition. Let's go to the lemma. First lemma. Left multiplication by a change of basis matrix for B and D converts a representation with respect to the first basis to one with respect to the second basis. On the other hand, if left multiplication by a matrix changes bases, m times the rep B of V is equal to the rep D of V, then m is a change of basis matrix. Okay, you can read the proof here if you like. I like to think of this in terms of basis element by basis element. So what are we trying to show here? Left multiplication by change of basis matrix for BD converts a representation with respect to B to one with respect to D. Let's see what this matrix multiplication does basis vector by basis vector. Okay. If this is true for all the basis vectors, then it will be true for all the vectors by linearity. Okay. So let's multiply the representation with respect to B of basis vector beta 1 by this matrix rep BD of ID, which is defined by this relation. The columns are given by the representations with respect to D of the basis vectors B1 through Bn. Okay, so I'm going to multiply this matrix times the representation with respect to B of vector beta 1. Now, what is the representation with respect to B of vector B1? Well, that's the first basis vector. The representation is just going to be 1 times beta 1 plus 0 times beta 2 dot 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 up to 0 times beta n. So the representation with respect to B of the first basis vector is this column vector 1 0 dot 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 0. Now here I'm just repeating the definition for the representation with respect to BD of the identity matrix. That's the definition that was on the previous slide. And if I do this matrix vector multiplication, you can see that it will pick out the first column in this matrix. Just try this entry by entry and you'll see. If you multiply across times this vector down, this 1 is going to pick up the first column and all the other columns will be zeroed out. So here we have that this matrix that we've defined times the representation with respect to B of the first basis vector gives me the representation with respect to D of the basis vector, because it picks out this first column. Now, that's true for any Bj. That's true for all beta j's. Okay? And since it's true for all basis vectors, it's going to be true for all vectors by linearity. So that takes care of this first part of the lemma. On the other hand, if I want to go the other way, suppose M acts in the following way on representations of vectors with respect to B. Suppose you multiply M by a representation with respect to B, and that gives you a representation with respect to D. Well, what does that tell me about M? Well, M times the representation with respect to B of the first basis vector is equal to, I'm writing M as its columns. That's the first column of M, second column of M, nth column of M. If I multiply this matrix times this representation, which again is 1 and all zeros following, that's going to get me the first column of M. And here it told me that M times the representation with respect to B of beta 1 should be the representation with respect to D of beta 1. So this information tells me that M times this representation will give me this, which will be equal to the first column of M. And similarly for all the columns of M. You just do it, instead of for beta 1, you do for beta 2, beta 3, dot, 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 up to beta n. And that will tell you that every single column of M is equal to the representation with respect to D of the corresponding basis vector. Okay, so that gives me the second part of the lemma, and that establishes my result. So what does this mean? This means that if I have a vector v with respect to a certain basis B, and I want to change it, I want to figure out what that vector v is with respect to a different basis D, I just have to multiply by this matrix, and this matrix is obtained by taking the representation with respect to D of each individual basis vector in the original basis. Okay, let's do an example. We have two different bases for the polynomials of degree 2. Now remember, polynomials of degree 2 has dimension 3. So here's one basis, 1 plus x squared. You can see that these are linearly independent because only this one has an x squared component. And you can work your way backwards. Okay, and then this one also has 3 vectors, and you can show by matrix arguments that these 3 are linearly independent. Okay. One thing you can see is that only this has an x component, and then these 2 are obviously linearly independent. Okay. So let's compute the representation with respect to these pair of bases of the identity matrix. So how are we going to do that? Well, remember what the prescription is. To get this matrix, we have to take the representation with respect to D of every one of the basis vectors in B. Okay, so that's exactly what he's doing here. I'm taking the representation with respect to D of the polynomial 1. And you can verify that to obtain 1, in terms of this basis D, you'll have to take minus 1/2 times x squared minus 1 plus 0 plus 1/2 times x squared plus 1. All right, if you do that out, you do that algebra out, minus 1/2 times x squared minus 1 plus 0 plus 1/2 times x squared plus 1, you'll find the polynomial 1. And again, I'm not going to go over how you actually come up with this vector, but you do that by solving a matrix vector equation. Right. Similarly, you can find representations with respect to D of the other basis vectors in B. This is the second basis vector in B. This is the third basis vector in B. Okay. So these are the columns of my change of basis matrix. Okay. This gives me the first column. This gives me the second column. This gives me the third column. And let's see if this works. Well, consider this polynomial 2 minus x plus 3x squared. I need to represent this matrix in terms of this basis. Well, because this is 3x squared, I must have 3 in the last component here. So that will give me 3 here. And you can work your way backwards to find the other components of the representation. Similarly, I could find the representation with respect to V, of V with respect to D directly if I wanted to. Here's a minus x here, so for instance the second component would have to be minus 1. And you can verify that this matrix times this vector gives me this vector. Okay, I invite you to verify that on your own. Let's just do the first one. You have minus 1/2 times 3 is minus 3/2, plus minus 1/2 times 4, which is plus 2. The minus 3/2 plus 2 gives me 1/2. That checks off. You can check off all the entries similarly. So it all works out. It's all consistent. Okay, so here is the matrix multiplication. All right, next let's consider the question, what types of matrices can be change of basis matrices? Okay, so we have this lemma that says that a matrix is a change of basis matrix if and only if it's non-singular. In other words, if I have a non-singular matrix, I can find two bases such that this matrix serves as the change of basis matrix for those two bases. On the other hand, if I do have a change of basis matrix, it must be non-singular. So that second one is the easier one to do, to prove that a change of basis matrix must be non-singular. But remember that a change of basis matrix is the representation with respect to basis B and basis D of the identity map. Now the identity map is an invertible function, and we saw already that the matrix representation of an invertible function must be an invertible matrix. Okay, so that gives us this. The change of basis matrix represents an invertible function, that is the identity. So the matrix must be an invertible matrix. So that gives us the first part, that if a matrix changes bases, then it is non-singular. Now we want to show that if a matrix is non-singular, then it is a change of basis matrix. Okay? And the way we'll do that is we'll show that any non-singular matrix M performs a change of basis operation from any given starting basis and some ending basis. Okay, so we're setting a challenge for ourselves. Given any starting basis, we can find an ending basis such that this matrix M gives me change of basis. Now, if the matrix is the identity, then I'll choose the ending basis to be the starting basis. Okay. Otherwise, because the matrix is non-singular, this corollary says that we can find elementary reduction matrices that successively multiply this matrix to give me the identity. Remember, this simply corresponds to Gaussian elimination to reduce M to reduced row echelon form. Each one of these elementary reduction matrices corresponds to one row reduction step. Okay. Now, elementary matrices are invertible, and their inverses are also elementary. So I can multiply both sides of the equation and express M as a product of elementary matrices. Okay, first I multiply both sides by on the left by RR inverse, then I multiply both sides on the left by RR minus 1 inverse, and so on. So I'm going to peel off all of these R's and bring them to the other side, and that expresses M as a product of elementary matrices. Okay, so where are we going with this? If we can show that each one of these elementary matrices represents a change of basis, then we're just successively changing bases R times. Okay? And the net total will be a net total change of basis from original basis to some other basis. Okay? So we successively change bases by each elementary row operation. Okay? So let's see how that works. Okay? We have three types of elementary matrices. The first one multiplies the first one will always multiply the kth row. The ith row by k. This multiplies the ith row by k, and you can see that if you operate this on a column vector, it's going to multiply the ith row of the column vector by k. The second one exchanges row I and row j, and if I apply that to a column vector, it's going to interchange the entries I and j. The third one adds a constant multiple of row I to row j, and if I apply that again to a vector, it's going to do this to the column vector. Okay. So if I apply row multiplication, so it changes a representation with respect to this original basis beta 1 through beta n to another with respect to beta 1 through beta n, but I replace beta I with 1 over k times beta I. Why is that? Because this row multiplication multiplies the ith component by k, and if I multiply the ith component by k, that means I have to multiply by a vector times 1 over k to obtain the same result. In terms of the beta I basis, this term is ci times beta I. In terms of the basis where beta I is replaced with 1 over k beta I need to multiply here by k ci. So if you look at the components, all the components are the same except for the ith component, which is multiplied by k. So in other words, I have changed from this basis of betas to this basis with sole change that beta I is replaced with 1 over k times beta I. Okay, so that takes care of the first type of elementary matrix. Second type, by row swap, simply if I row swap if the matrix does a row swap, I'm simply swapping the two basis vectors. Okay, so it's the same basis written in a different order. So this representation of V with respect to the basis in this original order is equal to this basis vector in the revised order, but I have to swap the two entries here. So this change of basis corresponds to the change in the coordinate vectors that is shown in this slide here. And you can do the last one similarly. Okay, it's the same sort of argument. Okay, so to recap, we've shown that every single one of these elementary matrices represents a change of basis, and if we multiply change of bases matrices one after the other, that represents a net change of basis. Okay, so any non-singular matrix can represent a change of basis. Okay. All right, corollary, a matrix is non-singular if and only if it represents the identity map with respect to some pair of bases. Now, why is this true? Because this is exactly the definition of a change of basis matrix. The change of basis matrix is a representation of an identity map with respect to that pair of bases. Okay, let's stop here.